Einstein said we couldn't tap into a nucleus for energy. Challenge accepted! So how can we tap into the energy of a nucleus? It's microscopic. That would mean the energy in it is very little and amounts to nothing, right? Wrong. A nucleus is made of protons and neutrons packed together, and that's good, but how in the world do two positive protons stay put together without repulsion? It's like trying to stick two like poles of a magnet together, but it can be done by a force called the strong nuclear force. It's basically like Iron Man trying to keep the Avengers team together, but the strong nuclear force keeps the nucleus together. This energy used to make the nucleus is called the binding energy. Elements with high binding energy are highly stable, duh. Heavier elements gradually start to become more unstable because of their radioactivity. If we take a heavy metal, let's say uranium-235 for instance, its total mass of the nucleus and the sum of the individual masses of the nucleons is not the same. This phenomenon is called a mass defect. It equals the sum of the masses of protons and neutrons subtracted by the mass of the nucleus. Using E equals mc squared, the mass defect can be used to calculate the binding energy. Thanks, Einstein. We chose uranium-235 because it's an unstable heavy metal with lots of nucleons, which equals boom! Not so fast, champ. We must first find a way to break the nucleus to release the binding energy, and that's where the fact that this element is fissile comes into use, which means uranium-235 can have its nucleus broken down by any neutron that has energy. Neutrons from cosmic rays should get the fission process started, but what kind of a process is it? Just like when a white snooker ball hits other snooker balls, making everything on the table move, one thermal neutron can hit the nucleus of uranium-235 and transfer its energy to form an extremely unhappy and unstable uranium-236, which splits into stable krypton and barium with 3 additional thermal neutrons. These neutrons in turn hit nearby uranium-235, causing a chain reaction. Even though splitting of just one atom of uranium-235 might not release the most energy, keep in mind that there will be a chain reaction taking place that releases 3 thermal neutrons that can potentially split 3 more nuclei for every single nucleus that has been split. When scientists did the math, it was shown that fission of 1 kilogram of uranium-235 releases 24 million kilowatt-hour of energy. That is enough energy to power a nuclear bomb. But we don't want a bomb. We want clean energy from nuclear power plants. To keep the energy in control, we have to pull out the NOs and stop half of the uranium-235 from taking part in fission. It's possible in a lot of intuitive ways. Think about it. And there we go! We showed Einstein it's possible to tap into the energy of a nucleus, and it's all thanks to his equation, strong nuclear force, mass defect, binding energy, and science!